Did you go to Lecture Helper? Are you in? Oh.
Sorry. I also forgot to mention you need to subscribe to this class. So the class name it's in the email I sent, but the class name is CS225. I'll write it down. And the key is CS225 SP17. So I'll definitely write that down.
Oh, I can do it. There is a space. CS, is it a lowercase?
Oh, no, that's right. And then 225. And then it's lowercase cs 225 SP17.
So these are caps right here?
Yeah.
Okay. All right, so the only text that you need to register that is in caps is the CS in the box. So if you're using Lecture Helper, the class name is capital C, capital S, space 225, and then everything else is lowercase. And the key is CS225SP17. It's our little secret code. And you can ask a question. Who asked, is this working? Oh, wait, I'm not allowed to do that. It's supposed to be anonymous. The answer is yes, it's working. Wait, this is going to be interesting. Okay. Yeah, let's go. Okay. So raise your hand if you have read the spec for MP3. Just curious. I need to know. Okay. If you haven't, it's probably a good idea to do so. So the MPs over the semester are difficult in different ways. So they're just all a little bit different. I think the special thing about MP3 is that you will spend more time debugging on it than any of the other MPs. So, yeah, because debugging is kind of this endless task, you don't really know when you're done until you're done. That's all the more reason to start early. So, MP3, lots of debugging, go. Exam 2 is live for you, and it actually goes just through tomorrow. I don't know why I thought it went through Wednesday, but I think that shouldn't make a difference to you because the scheduler has had the right dates the whole time. It really just goes through tomorrow. Okay. All right. So I want to plunge into the material. As you are well aware, this is the second lecture hour of the day that I do. And in the first lecture hour, we made it through that many slides. Okay? Yeah. So, I'm always optimistic. I guess it's probably a good time to say that the fact that I print off a whole bunch of them and we never get to all the slides doesn't mean we're skipping the material. I will always pick it up in the right place the next time. So don't worry, we really do end up covering it all. It's just, true confessions. My biggest fear is running out of stuff to talk about. So, that awkward silence, I hate it. So that's why there are always too many. Okay. So let's talk about the content for today. I'm actually very excited about today because today marks the day that our focus shifts from C++ intensive instruction into data structures. So what we're going to be doing from here on is a much more classic approach to data structures, or the way that you store your data in a clever manner, the way you are clever with your data, and the algorithms that you use to access it. So, yay, I'm quite excited about it. All right, that said, C++ never really leaves us behind, and so I'm going to try to remind you of the salient points as we see them. The things that are hard about C++ or that are easy to forget, I will bring them up again. Okay, so we're going to begin today's discussion with a new structure that we're going to refer to as a list node. Now, I want to remind you that a struct is really just a class where the access is by default public. And it really is true that a struct is that. In fact, you can put functions inside a struct if you want. There's proof of that on the board because look what I have here. What is that? It's a constructor, that's right. So you can put constructors inside structs just as if they were classes. You can have private sections to structs. The only issue is that, or the only thing that distinguishes it from classes is that the members are public by default. That is, if you don't put them in any block, they are public. That's it. There is one key portion that I have left off of here just to remind you, and that is this. In looking at the class itself, or the struct itself, what do you think the parameterized type is going to be called in this example? Can you tell? Can you guess what I'm going to use for the parameterized type? Somebody raise their hand to tell me. Yeah? Yeah, LIT. Right. List item type is kind of what that came from. Okay. So that means the focus of our discussion is not going to be on the type of thing that our structure holds, but rather the structure itself. In fact, if there's ever a doubt about what kind of thing we're putting in, I'm probably going to default to integer. I'm probably just going to use examples that include integers. Ho hum yawn, okay? Because the focus instead is on what this thing looks like. What it looks like in memory, what it looks like in the sketches that you draw, and the way that you model it inside your algorithms. Okay, so let's start there. I have this new struct, and I'm going to declare a thing of that type. Let's see, list node x list node x, and my constructor wants something, so I'm going to give it 5. Okay? So now think about what this does. This builds something that looks like that. I'm going to use little rectangles to draw those things, like this. The first part of it is the data. The constructor takes the input data and plunks it there. And the second part of it is a list node pointer whose value upon initialization is null. So when we make this declaration, the list node x5, what we get in memory is this. Are there any questions? Have I done this correct? Yeah? Oh, darn it, you caught me. Okay, so here's the deal. I am almost always going to forget the template, okay? And the way to let me know that I have done this, I mean, you could do this inside Lecture Helper if you wanted to, but if you decided not to use Lecture Helper, what you can do is go like this, and I will go, oh, yeah, right. We need the template information. So in this context, I should have added... yeah, I don't know, isn't it kind of cool, actually? It's like we're being cool. It's like we're being geeky cool. I know, I think it's awesome. We should have added this. Now, here's the thing. If we aren't explicit about it, the compiler will probably figure it out based on the type of thing we put here. If we added another constructor that had no parameters, then things would get more complex. The compiler would say, hold on, wait a minute, it's a templatized class. I don't know how to build the thing. And you would have to, in fact, specify the parameter. I'm sorry, the type parameter. Okay, so let's see. Oh, so I will almost always forget this. And the way I want you to think about my error is kind of like you think about the error that I make when I forget a semicolon. Like if I were to forget a semicolon, probably what you'd go is, oh, yeah, she just made a mistake again, and you'd let it go by. I want you to feel kind of the same way about the angle brackets. That, you know, the compiler's going to help you out if there's a mistake, or, you know, I didn't have screen space to write it down, and I knew you guys were past it. So I want you, like, not to be like, you forgot your angle brackets, because I know I'm going to, okay? You can do this, though. That's fine. And you can do this, you forgot your angle brackets if you want to, but I might tease you back about it. You forgot your angle bracket. Okay, so let's make this a little bit more interesting. Okay, now, so I'm going to remind you that what we have here is this right now, this little chunk of memory, part of which contains a 5, right here, because of this, and part of which contains a list node, as in this kind of list node, but a pointer. Now, C++ demands that we use a pointer in this context because if we didn't, we would have this kind of recursive definition and we go, whoa, wait a second. I don't have a list node class yet. You shouldn't do that. And so we're using the pointer to kind of buy us this opportunity to instantiate these things as a target on the heap. Okay, so now, instead of declaring a list node on the stack, we are going to make it so list nodes are always handled like pointers. So what I would like for you to figure out and for you to help me with is if I want memory to look like this, that is, if I want a list node pointer whose name is y to result in memory that looks like this, I need you to help me write the code. So write the code that would declare and initialize memory so as to look like this. Okay, take a couple seconds to do it. And don't let your neighbor see, okay? Hide your work from your neighbor. Put a little wall around it. Don't let your neighbor see. Keep your secrets. When you think you're done, then let your neighbors see and see if, moreover, peek over their shoulder and see what they did. See if it's the same as what you did. If your neighbor did nothing, let's see, I don't know, what could we do? Poke them. Come on. All right, so let's work on this together. I'm going to answer this, but what I need to know from you is what's the first letter that I'm going to write? What's the first letter that I'm going to write in the solution to this question? How do I configure memory like that? First letter I'm going to write is L is correct. I think I can spell the rest of the word. List node. Now what? Pointer, or asterisk, or splat. Okay. What's the next thing I'm going to write? Say it all together. Y. This is a philosophy class. Good. Oh, I did the assignment statement for you. What's the next letter that I'm going to write? Say it loud. N, good, okay. New, list node. Now things are pretty familiar, right? List node looks like an 8. Okay? All right, any question about that at all? Is it clear? Yeah? Don't I need the brackets with the int? So the correct way to tell me that is by doing this. Yeah, thank you. Okay, yes, you're right. Probably in this case, again, the compiler would infer it, but it's always best practice to include it. So you're right, darn, I forgot again. And so I'll add them where it's necessary. Okay, I'm going to forget them all day, I'll tell you. I didn't even do it on purpose there. Oh, it's your fault. Oh, I'm always happy to blame somebody else. It's not a good practice to blame students, though, probably. Okay, all right, so I like this a lot. Now, what I want you to do, the very next thing I want you to do is write additional code so that this is used and memory is the result is configured like this, so that this box is the same piece of heap memory as the one that you just asked for from new, okay? So go ahead and write the code that you need to now make memory look like this instead. And you're welcome to use Y. When you're done, put your finger on your nose so I can see when people are done. You can do it casually if you want. Oh, I'm not done. I shouldn't put my finger. Did you guys both write the same thing? You're both done? Okay. Okay, take a look at somebody sitting close to you. Now what I want you to do is raise your hand. If you did this, raise your hand with the number of lines of code that you wrote to do this. So 5, 4, 3, 2, 1, 0, because I used ESP. Okay. All right, raise them high so you can all see. Okay. All right, I'm going to write the lines of code that I did, and I bet you will do that some of you will have done. Oh, no, maybe, yeah, maybe these will all be the same. Okay, so I'm going to declare pointer z, and so I'm going to say list node pointer z equal new list node 6, because building this piece of it is very much like building that thing to begin with, right? And then all we have to do is add on y. What should point to the same place as y? Z next, good. So z's next equals y. So this value, this pointer, should point to the same place that y did. Okay? Yeah, angle brackets. Gotcha. Thank you. Yes? How come z isn't a double pointer is the question. So z is a pointer. What kind of thing is its target? its target, that is, if I dereference Z, which is what this does, if I dereference Z, the thing that I get is a list node, not a list node pointer. Okay? Is that distinction clear? Okay. All right. Any other questions about this? I'll remind you that this is a dereference. So what this little piece says is start at Z, dereference. So now we've got this box, and take the next field. That's the one that we're going to change. Okay? How are you doing? It's okay? All right. I think that it would bother you if I asked you to set up a chain of 10 of these things, right? Like it would end up being a lot of kind of busy work, allocating the memory and assigning them one at a time. All right, notice that what we've done here is we've used the new statement twice, 2 news. And memory looks like this. Where does Z live? Stack or heap? Sorry, is Z on the stack or heap? Z is on the stack. The fact that it has a name, the fact that I could say where is Z means it's on the stack. The named variables are on the stack, okay? On the other hand, the memory associated with Z, Z's target, is heap memory. How do I know that's true? That keyword, okay? Similarly, for the memory associated with Y, because we use that keyword again. Do that, okay? We use the new keyword again. Now, because we asked for that memory from the heap, we better be willing to give it back. All right, so what I want you to do here is write the code that would free up that memory. So this is what memory looks like. It's got a stack variable Z pointing to, this node. Its next one is this node, and Y is still sitting there, okay? And I'll give you the hint that the 2 lines of code that you're going to write both start with a D. And the whole question is, what is the D? Delete. What is the delete deleting? I'm going to put a little green blob in here because I'm admitting that I forgot those. Yeah? No. All right. Here's what I wanted. Here's what I'm going to assume, okay? I'm going to assume you wrote 1 line of code that frees up this memory, and then that you wrote 1 line of code that frees up this memory, okay? And what I want to know from you is which one did you do first? That is, which delete statement comes first? Raise your hand if this is the first one you delete. Okay, good. And raise your hand if this is the first one you delete. Okay. All right. In this case, there are a couple different ways we can write the delete statement. I'm going to address that distinction in just a second. We could say delete Z's next and then delete Z. Or alternatively, we could say delete Y and then delete Z. Those are effectively the same. It's just an issue of which pointer do you use to free this memory, okay? Now, if you use this first option, and you say delete Z next, you are invalidating y. You're invalidating y out from under it, right? You are, for a brief second, taking this and completely invalidating it. Wait. If you say this one first, it means that this pointer is invalidated, and the fact that you have a y is actually just lucky. Because if you delete this one first, you've invalidated sort of your A main handle on this other one that you're going to need to delete. So here's the thing. The fact that we have y here kind of saves us. If we didn't have that y, we would virtually have to delete this one first. Okay? Because if we didn't, we'd lose the ability to find it. If we delete this one first, we may not have access to this handle on this box. I could not have jumbled that up anymore. I apologize. Let's see, how can I fix it now? The question on the floor is, why does the order matter? In our context, the order we delete those things doesn't matter because we have a handle on both via z and via y. If we had no y and we deleted z first, then we would have lost access to this one. So it's just by happenstance and good fortune and the basic setup that we have that we're lucky enough to also have a handle on this second one. Because that's true, it doesn't really matter what order we do it in, but we were just lucky. Okay? Yes? Yep. For this case, you could have done delete z, then delete y, but we would only have been lucky to do so. Sorry. Okay. Let's see. So let's move on to, I think, something a little bit more. So here's what we're doing. We're going to assume that somehow we have built up a whole bunch of these things into a chain, okay? And the first thing of that chain, the first list node pointer that we have a hold of is called the head, okay? We're going to assume that we have a whole bunch of them built up. Now, here's the code that we're going to write. We are going to write a little piece of code that takes a pointer here, a handle on one of these chains, and a new value to insert, and puts it in at the front of that chain, okay? Just inserts it at the front. Now notice that if we do this right, we're actually giving ourselves the way to build up a chain, right? Insert at front could actually be used. We could have gone insert at front, head pig, insert at front, head cat, insert at front, head dog, etc., and built up that chain. So the fact that we're doing this kind of special purpose function is actually kind of okay in this context. It's going to be very useful to us. For now, this is the way we're going to do things. For now, we're going to initialize our lists in exactly this way, kind of one at a time. Okay, let's see what that is. So the question is, how do we do this? Now, the way I like to plan for writing code like this is to draw a picture of how I want the memory to look after the function is called. So I'm going to sketch, with this pen on this as if it's paper. I'm going to sketch what I want memory to look like, and then I'm going to write the code that I think will make that happen. Okay? So bear with me and do this yourselves. For this reason, I really strongly suggest that you get a pen. If you don't happen to have a tablet, get a pencil and a pad of paper, especially as you do MP3, and be willing to sketch these sort of chains of memory. Okay, so what I want to be the case after we do this is I want a new list node. whose value is cow, whose data is cow, whose next pointer points to dog, and in the end, I want head to point to cow. So I want to change my chain so that it goes cow, dog, cat, pig. Okay, any question about that? It's all right? Okay, now let's write the code to make it happen. As I write each piece of code, I'm going to kind of color it in on my drawing to show that I've done it, okay? All right, so what do we have here? Well, head becomes cur and cow becomes e. Okay, I know how to deal with that. I know that I'm going to need a new list node, so I'm just going to do, I'm going to create a temporary one called t, list node pointer t, yeah, angle brackets, I know, list node, and into it I'm going to put whatever e is. Okay, so now I have this part, okay, and cow is in there by the constructor. Now I'm going to say t next equal cur. So that gives me this part, right? Yes? It's the target of these things that are identified. Okay, the target of these things are made the same by that assignment. And now finally, oh, semicolon. And now finally, I need to change head. That is, I need to set cur equal to t. And now I get this part. Okay? Okay. What do you think? So we're going to have an awkward silence here because I've made a huge blunder. It's a huge blunder. And I want you to figure out what it is. It's subtle. It's common. It might be the first time you've ever seen something like this, and it has absolutely nothing to do with, okay? Ignore those. Yeah? Do cur and head point to each other? Current in the heap? Current and t. Oh, do current and t point to each other? I don't think so. I mean, they point to the same node. They do point to cow, but we don't care about t. What happens to t when this one finishes execution? It goes out of scope, right? So we're not, you're right. You are absolutely right. Current and t point to that same node, but that's okay. Okay? That's in fact what I meant to do by this last assignment. Okay? That's good news, actually. Okay? Yeah? Yep. So the data is on the heap, but the means of accessing it is t. So I said t equals new. So the box is in the heap. The box is in the heap. When the function completes, t goes out of scope. T goes out of scope and the box is still there. That's fine because that's what we want for head, right? Yeah? Oh, what? Ah, good. So did you all hear him? He observed two things. T is a local variable. It goes out of scope. Cur is a local variable. It goes out of scope. Head came in, right? And it became, we got a copy of head. So, all right, so let me trace it more carefully. We copy, cur is a local thing. Here it is. I'll put it in a different color. Here it is. Here's cur. It's a pointer. When we pass in head, it becomes a copy of head. It points to the same place as head does, right? We copy the memory address. We copy head's value, which is a memory address. And then we fix up cur. We do this. Yay. Just like we want to, right? That's the right thing. But then cur goes out of scope. So what's head after this completes? Still points to dog, that's right. Head still points to dog after we execute this function as it is. Moreover, we've got a memory problem. What happens? We leak that new, right? Because we've removed all of means of accessing it. So how do we fix this? How do we fix it? Yeah, way in the back? Very good. Very good. So think about what passing by reference does. It gives another name for the parameter, for the value of the parameter. So if we want to change that pointer, then we should just give another name to head. We do that by passing that pointer by reference. I think this is the first time in this semester that you will have seen passing a pointer by reference, but it won't be the last for sure. Okay? All right, how are you doing? I looked at the lecture helper thing. I would know if problems were pouring in here. Okay, any questions about it? Okay, you're good? Okay, so this is okay. What's the type of the thing? It's a list node pointer. How are we passing it? By reference. That's what this function signature says. Okay? All right, really, no questions? You're good? Yes? So an alternative solution to this problem would be to build the pointer, to build T, right? To build that node that we want and return it to the calling function. But in that case, this would be different. It's a different interface to using this function. It's an alternative one, and it's fine. It's just different than what we have here. Okay? All right, any other questions about this? We'll see that one occasionally as well. You're good? We're fine? Okay, you guys are so smart. Okay, fine. I love this because I get to ask you for the first time this semester, what is the running time of doing this? What's the running time of that function? And when I ask the question, what I want to know from you is, how does that running time vary with respect to the amount of data that the structure holds? Okay, so the things you should be asking yourself are, what's the difference between this thing holding 3 pieces of data and it holding 3 million pieces of data? So what is the answer to that? Yeah? Yeah, this thing runs in the same time, no matter how much data the structure holds. The way we describe that is to say that it runs in constant time. So the running time is constant time. Another way of writing that is big O of 1. Maybe I could have shocked you by saying big O of 14. That would have been okay too, right? All we need to know from this statement is that there exists a constant so that the running time is always less than this times that constant, okay? So the point is, we don't know for sure how fast this thing runs, but we know that there is a fixed amount of time beyond which it will not go over. Moreover, we know that that running time is not changing, is not different, whether we have 3 pieces of data or 3 million. Now, When you look at the code, how do you know this is true? What's a dead giveaway about this code that kind of verifies our instinct that this does not depend on the amount of data it holds? Yeah? Yeah, no loops is a huge cue. No loops, also no recursive calls, sort of the same story. Moreover, each piece of data is the same size. We don't have any arrays that we're assigning back and forth here. No arrays are coming through our parameter list. We're not copying big pieces of data. The way I would wave my hand to describe it is to say, oh, look, this is just 3 little assignment statements. Okay? All right, any question about that? If you have forgotten about this definition, you should go look at your discrete math notes. Yes? That's a good question. So should you write big O of C? So then you would have to, so you could, but you'd have to do it like this. You'd have to do it, there exists a C such that big O of C, and actually this little piece is part of the definition of big O. So you don't need to do that actually. You can choose any value that you want, and the existence of this C, which is this times whatever we write here, is guaranteed by the definition of big O. Okay? So you could, but you'd need to do this, and you don't have to. Okay? All right, any other questions about this? Okay, yay. I've got another one for you. We learned a lot here, right? Like we saw something interesting, I think. Okay, I've got another one for you. This time we're going to exploit the following. I have here a big chain of these things, 8, 4, 2, 6, 3. And what I want to observe about the structure of all of these things put together is either this chain has nothing in it, or it's going to be it's going to be something followed by a chain. Now notice what I just told you. I basically told you a recursive definition of one of these chains of memory, right? I either said, I said either it's empty or it's a node followed by a chain, okay? Now the question is, how can we exploit this recursive description of the structure in such a way that we can write an algorithm to solve a problem? Now, the problem that we're going to solve is simply to take the values in that chain and print them out in the reverse order. And the observation is simply this, that if I've got a chain with those 5 values, to print them out in reverse order, I'm going to print this out in reverse order, that is the rest of the list out in reverse order, and then I'm going to print the 8. Okay? Now, I'm going to assume inductively that I've got a function that works on this. The result then is if I print reverse of the rest of the list, I'm going to get 3, 6, 2, 4, and then I add the 8 at the end. Okay? Any question about that? And it pretty much prescribes the way that we should solve this problem. Okay, so here's what I would like you to do. I want you to not peek at the code I write. I'm going to write some code. I want you to write the code that solves this problem, assuming that head is passed in. Don't worry about, and I'll tell you via heads up right now that you don't need to worry about passing by reference. We'll talk about it later if we have time. Okay? I'm not sure we will. So I want you to kind of focus on your own code and then peek at mine. I'm going to want to know if we did it the same way. We can take that. Yeah, you can assume the IO stream. Okay, you can peek anytime you like. Okay, should we talk? You ready to talk? Okay, I'm going to go out on a limb. I'm going to ask you to raise your hand if you used a different base case than me. Okay, so raise your hand if you used a different base case than me. Raise it high so I can see, please. Raise your hand if you used a different base case. Okay, good. And those of you who used a different base case, can you tell me whether you used one or two base cases just by raising your fingers? One base case or two base cases? Okay, and for those of you who are saying you used one base case, let me ask you this. Does your solution work on an empty list? Does your solution work on an empty list? That is, if I pass in null to it. Does it work? Okay. All right. It's a little bit of sleight of hand by me. I wasn't particularly careful to say that, you know, an empty list is a list or an empty chain is a chain. I wasn't particularly careful to say that, but this case, using, oh, well, where is my base case? Oh, I don't have a base case. Where is it? Where's my base case? It's the empty list, right? And what do we do if we have the empty list? Nothing, right? So I have this sort of implicit base case, okay? Anytime you can do that, you kind of cut down the number of test cases you have to have, right? Kind of. Okay, so how does this work? You come in, you on a list of length 0 or a list of, or a chain of 1 or 0 things, that means cur is equal to null, nothing happens and we're done. How does it work if you have one thing? Well, it makes a recursive call. What does that recursive call do? Nothing, right? It makes the call, but then that value is null, so it does nothing, and then it prints out that single character. So this code handles, as a general case, the single node chain. Okay? All right, any questions about it? Any questions about this little piece of code? Okay. Does the running time of this thing depend on the number of elements in the list? Oh, yeah, it does. How do you think it depends on the number of elements in the list or chain? How does it depend on it? What does it do for each element? It prints it out and it makes a recursive call, right? It makes a recursive call and it prints it out for every element in that list. Now, both of those, in and of themselves, are constant time operations. So we're doing a constant amount of work for every element in the list. The way we describe this, and I'll talk about it in more detail next time, the way we describe this is a constant amount of work. Here's the key part. I wish I had italics or bold. Per data element implies what we call big O of n, where n is the number of elements. This is also referred to as a linear time function. And my clock says we're done. We'll talk about it more next time. 3 slides. We did 3 slides. Shocking.